Hello and welcome to all of you for today's lecture. So today we'll see some examples on electrophilic substitution on the 5-membered heterocycles containing one heteroatom. The first example is this 3-methyl furan is treated with HCN in presence of HCl followed by hydrolysis. You get the formylation. Now this reaction is formylation reaction, and HCN HCl is going to be a reagent combination this. So first of all, the available positions are either this or this. So let us say that this is attacking on this, and then the driving force is protonation. So as a result of this, we will be having say O, and this is going to be CH3 plus, this is stabilized by hyperconjugation also, NH. The loss of proton followed by hydrolysis will furnish the desired compound, that is. So this imine is labile to acid hydrolysis. So you have to just simply put this sign and put water. So it will, first of all, it will generate geminal diol and ammonia will go off, and you get the aldehydic functional group at this point. So once this product is given, you have to see that methyl group is orthopara directing, and this is ortho position. In addition to that, this carbonium ion is stabilized by resonance as well as hyperconjugative effect of methyl group. So the collective stabilization gives this product as a major product. Okay, moving on to the second example. Now second example is Pyrrole treated with sulfuryl chloride, and you get the chloro compound. Now this has to be a source of this is SO2 Cl2. So once let me put Pyrrole here, you can directly show the attack at sulfur. This will go off, this acts as a electron sink, and then you can show the S double bond O Cl plus. Then the Cl minus can help in abstraction of this, and then you have to show the attack. Maybe we are just proposing the mechanism. SO2 Cl, so maybe Cl is coming here, and this will give rise to loss of SO2. So that will be your chloride as a product. So SNI type thing. So sulfuryl chloride is also the reagent. Third example is this Pyrrole 2-position ketone, iodine and Ki. So probably the role of Ki is to polarize the iodine and then make the I plus available. Now this is meta orienting. So with respect to this ortho and meta, so this position is available. So first of all, you have to write down the compound. Now this is the meta orienting group, this position is available, and what we can show is it will plus delta minus delta, let us say, and then this will go off. So some polarization is there, and because of that it will be COCH3. This double bond is intact, and then it will be I plus, and of course the I minus can abstract the proton which is already there and help in the aromatization. So that is how you get the compound. So the weakening of I bond, interhalogen bond, and then that I minus which is going out can help in the abstraction of proton, which is necessary for restoring the aromatic sextet. Okay. The next one is, this is peculiar reaction. Now there should be positive charge here because 4 bonds are there. So methyl iodide excess means this will undergo methylation, that is first step, and of course all methyls you will get, and this plus polyalkylated complex. So this compound is not easy to alkylate because this has got some side products. In addition to this you get polyalkylated compound, so that is the problem. But in this case, in Pyrrole you get the meta substitution because this is meta orienting group, and the ordinary mechanism suggests that if I complex this with LCl3, there will be formation of ion pair complex, and then in this compound what we have, the meta position with this is meta orienting, so this comes and attacks. Now the secondary cannot reorganize because that is the maximum stabilization one can have with this carbonium ion. This AlCl4 minus can help in the aromatization. So that is how you get the target molecule. So in case of all Friedel-Crafts alkylation reactions, the formation of carbonium ion can take place by 3 different methods. One of them is to treat the alkyl halide with Lewis acid. Second is to treat alcohols with mineral acid. Third is to treat alkenes with H plus mineral acid. So those are the different methods to generate the carbonium ion, and carbonium ion is going to be the effective electrophile in this Friedel-Crafts alkylation reaction. It can be any substrate for that matter, not necessarily the Pyrrole, but any aromatic compound you can bring about the alkylation reaction with varying degree of stabilization of carbonium ion. The most stable would be tertiary. If the structure permits, secondary becomes tertiary, or primary becomes secondary, and so on. The next example is this chloroform, KOH and Pyrrole. KOH or any base you can use, say sodium methoxide, potassium tertiary butoxide, etc. The role of KOH is to bring about the 1,1 elimination. So this comes here, this goes out. So this is alpha elimination or 1,1 elimination you can say. So this will give rise to chlorocarbon. Now this chlorocarbon has to interact with your compound, and with this what you get is this intermediate, or I can directly put the compound. So this is adduct. So chlorocarbon added to double bond, so you get this intermediate, and then with base I will get N minus. This N minus can come here, this can come here, this will go off, so that we get the formation of double bond, double bond, double bond, and single here. So that becomes 3-chloropyridine as a product. So first of all, the key step is the formation of, so 2 plus 2 adduct. We know that carbines can add to double bond and form the cyclopropane. This is dichlorocyclopropane derivative, and then you can easily abstract the proton. This is acidic, and then you can bring about the elimination of Cl minus. That is how you get the 3-chloropyridine as a product in this reaction. Okay. Now we will see a couple of examples from thiophene. The first one is thiophene is treated with acetyl nitrate, and you get 2 nitro compound. This is the nitrating agent, and the reaction is carried out at 10 degrees Celsius. The first foremost thing is the 2 position is substituted. So when this kind of attack takes place, you get carbonium ion at 3 position. The acetoxy group which is coming out can abstract the proton, and this becomes acetic acid, and you get the substitution at 2 position. The next example is 2-carboxylic acid derivative of thiophene treated with HNO3 H2SO4. Now this is being electron withdrawing group. You can use the conventional nitrating mixture, and this nitrating mixture also makes the nitronium ion, that is the active electrophile. The sulfuric acid being strong acid than nitric acid, so this can abstract a proton. So proton donor is acid, proton acceptor is base. So that is relative acidity, basicity amongst these two. So this is conjugate base, this is conjugate acid. So this is conjugate base, and this eventually loses water, and you get the nitronium ion. Now this nitronium ion can interact with the substrate. This is meta orienting group, so it will attack at meta position. Eventually you will have the carbonium ion here, and then HSO4, which is a conjugate base, helps in the aromatization of this substrate, and that is how you get the incorporation of NO2 group at meta position with respect to this. So it will be 1, 2, 3, 4 nitro derivative of this acid. So the formation of nitronium ion, we know that it is being evidenced by the factors like this is the linear triatomic molecule which can give lines in Raman spectrum. This is Raman active, not IR active, because this is linear triatomic, the dipole moment is 0. So this will appear in Raman line, and you get the strong line around 1400 reciprocal of centimeters, and then that is the evidence for the formation of linear triatomic molecule. So that is there. So I think we can do one more example here, and we can conclude the things for today, and then next time we will continue from here. So I will put one more example from thiophene, of course, that is thiophene sulfuric acid. You get thiophene sulfonic acid. Okay, so thiophene sulfonic acid. Sulfuric acid, we have already mentioned that this is the combination wherein one sulfuric acid functions as a base, the other function as an acid, and then let us say that this is base which will abstract the proton, and then eventually you will have, let me put it in the condensed form. This becomes HSO4 minus, this becomes OH2 plus, SO and OH minus H3O plus, and then you have, so the overall thing is 2 H2SO4 molecules, they give H3O plus SO3 HSO4 minus. So 4 hydrogens, 2 sulfurs, 8 oxygens, so it is balanced. So this is the actual electrophile, this is neutral electrophile, and this neutral electrophile has to interact with your substrate. So SO3, the polarization is because of the sulfur oxygen electronegativity difference, and we know that this becomes SO3 minus plus. Of course, the HSO4 minus helps in the abstraction of proton, thereby we retain the aromatic sextate, and this eventually takes a proton from water and you get the sulfonic acid derivative. So this is how the electrophilic substitution takes place. So sulfuric acid is generally used, if not oleum is used. In case of acid sensitive compounds like furan and pyrrole, we use pyridinium sulfate, that is the another reagent which is used because that generates this electrophile in situ. So those are the new things. Next time we will continue from here, we will have more examples on thiophene, and if time permit we will do the nucleophilic substitution reactions on the substrates also. Okay. Thank you very much.